Hi everyone, this is Dr. K. Kannan, Associate Professor, Department of EC, R.M.K. College of Engineering and Technology. In this lecture video, I am going to talk about the Poynting theorem and the Poynting vector in terms of electromagnetic fields. So before that, the important topics we are going to discuss in this lecture video is group velocity, electromagnetic power flow, and Poynting vector. So group velocity is a wave, is the velocity with which the overall envelope shape of the wave's amplitude known as the modulation, or we can call envelope of the wave propagated through the space. Now look at that, the group velocity and the envelope of the signal. Now consider two signal. One is vary with respect to t, and another one also the same thing. The thing is that W1 is the first one and W2 is another one. The difference between W1 component and W2 component is entirely shifted by 180 degrees. So that the sum of this W1 and W2 is called the total. So this sum of the W1 and W2 is called the wave packet. It is composed of two frequency components showing the carrier and the envelope. The carrier travels at the phase velocity, whereas the envelope travels at the group velocity. So therefore, the constant phase wavefront travels at the phase velocity, but the group velocity is the velocity at which the energy information travels. Then, so what is the point to remember regarding phase velocity and group velocity is phase velocity we can give the equation Vp equal to omega by beta, or in another equation Vp equal to root of epsilon mu. So this is constant and it is independent of frequency. So when we consider the lossy dielectric where Vp is not a linear function of frequency, so this creates a distortion in the signal wave shape, so that we are getting distortion. The next one, lossy dielectric is a dispersive medium. So here the dispersion is the phenomenon of signal dispersion depends on the phase velocity and frequency. When group velocity it is information signal has a small spread of the frequency around the carrier frequency. So around the carrier frequency is it is sidebands. So such a signal comprises of the group of frequency forms the wave packet. The velocity of propagation of the wave packet envelope is called the group of frequencies. Then the flow of electromagnetic power and the Poynting vector. So here we are considering the electromagnetic wave that carries electromagnetic power, and the energy is transported by means of electromagnetic wave. Then we derive the relationship between the rate of energy transfer and the electric and magnetic intensities associated with the traveling electromagnetic wave. So this wave can be derived from Maxwell's first equation in point form is del cross H is equal to J plus dou D by dou T. And then we are going to dot product with the electrical intensity on both the sides, so that E dot delta H is equal to E dot J plus E dot dou D by dou T. Then we are taking the vector identity y because here in a equation, above equation we have dot and the cross in a single line, so that we go for vector identity. So the vector identity of E dot del cross H is equal to H dot del cross E minus E of del cross H is the answer for the vector identity. So that we can rewrite that equation according to our requirement E dot of del cross H is equal to H dot del cross E minus del dot E cross H. So we can substitute this value into there. Then we are going to get the equation as the H dot del cross E minus del dot E cross H is equal to E dot J plus E dou D by dou T. Then from Maxwell's equation 2, it is in terms of R dash R del cross E equal to minus dou B by dou T. So we are considering this equation by substituting 4 into 3, so that we are getting H of minus dou B by dou T minus del of E cross H is equal to E dot J plus E dot dou D by dou T. So we can rewrite this equation, and finally we are going to get the term in the right side of equation 5. It is E dot J, which is called the current density, and D is a flux density, and B is equal to magnetic flux density. So substitute all these values into the equation. We are getting del dot E plus H is equal to sigma E square minus E of dou D by dou T of epsilon E minus H dot dou by dou T of mu H. So that we can consolidate it as finally we are going to get the value which is dou by dou T of 1 by 2 epsilon E square minus dou by dou T of 1 by 2 mu H square. Then we are going to find out the above equation in terms of volume, so that we are taking the volume integral. So integral volume integral of del dot E cross H dV is equal to minus integral integral of sigma E square dV minus volume integral d by dt of 1 by 2 epsilon E square plus 1 by 2 mu H square. So that is the left side equation, and the right side you have two terms. So the first term left side represents total power, and the right side you are getting power dissipation. This is the first term, and the second term rate of energy stored. So that we are going for the divergence theorem useful to find out the surface integral term volume integral. So according to that theorem, the surface integral of d dot d is equal to volume integral of del dot d dv. So we can substitute substitute there, and finally we can rewrite the equation in terms of the surface integral in the left side. So the left side integral S E cross H ds. So right side as it is, but the left side only we are going to convert the volume integral into surface integral. So the left term represents total power leaving the volume, and next one ohmic power dissipation, and last term it is the rate of decrease of energy stored in the electric field. So to be constant with the law of conservation of energy, this must equal to the power leaving the volume throughout is the surface. Therefore, this the quantity E cross H is a vector representing the power flow per unit area defined by the quantity P is a Poynting vector. So P equal to E cross H meter per meter square. So that here the power density vector associated with the electromagnetic field, and this is not limited to the plane wave. Then in general the equation can be rewritten as the total power in a given surface is equal to sum of WE plus WM dV plus P sigma dV, where WE represents electric field intensity, WM represents magnetic field intensity, and the P rho represents the ohmic power density. So that the conclusion is if the medium is lossless, then sigma equal to 0, then the loss term of RHS from the above equation is going to be 0, and then the total power flow in the closed surface equal to rate of increase of the stored electric and magnetic energy in the closed volume. And if the medium is static, if it is not a dynamic, then the first two terms in the above equation vanishes, and then the total power flow in the closed surface is equal to ohmic power dissipated in the closed volume. So then we are going to find out the total power in a coaxial cable according to that equation. So consider here the axial coaxial cable, inner radius is the outer radius is B, and the current flowing through the inner radius plus A and the outer current is minus I. By using Ampere circuit law, the line integral of magnetic intensity is equal to I. So that here in the integral it is the circumference of the circular path, because we are considering circular conductor between A and B. So that it is integral dl is equal to 2 pi r. So h2 by r equal to L. So h equal to I by 2 pi r. Here r is ranges from A to B. Then already we derived from the equations of electrical intensity E due to law conductor E equal to lambda by 2 pi epsilon. Similarly, the potential also already we find out this potential difference V equal to lambda by 2 pi epsilon ln B by E. So that the electric field E in terms of V we can given by E equal to E divided by ln P by A of R. So we know that the total power density P equal to E cross H. So always perpendicular to each other. So that we are going to multiply E and H. Then the total power will be given by the integration of power density P over A cross the surface. So the total power equal to integral B by ln B by A R dot I by 2 pi R into 2 pi R. So we can solve it. Finally, we are going to get W equal to I. Therefore, the total power flow along the cable is the product of potential or potential difference and the current I. Thank you. Thank you, one and all.